Okay, collisions in one dimension. We mentioned earlier about the difference between we talked about an inelastic collision, and now we're going to talk about what that means. Starting off with a demo, I have here two seemingly identical balls, and I'm going to use them to demonstrate elastic versus inelastic collisions. Elastic collisions conserve energy. So if you drop a ball, it makes a collision with the surface, bounces back up, and if it comes back to the same height, that's what we call an elastic collision. An inelastic collision is one in which some of the energy is lost during the collision. And as you'll see with both of these balls, both will be inelastic because neither will conserve all the energy. So let's try this one first. Actually, I'm going to try this one first. Okay, so we know that it's an inelastic collision because the ball, having bounced from the surface, doesn't come quite back up to the same height that it started from, as you can see. This one looks identical, has slightly different interior structure. Now that one is even more inelastic. A lot of energy is lost in that collision. There's the transfer of kinetic energy into thermal energy. So this ball heats up a little bit because of the materials inside that damp that energy down. The most extreme case of an inelastic collision is a perfectly inelastic collision, and that is one in which you drop the ball and it doesn't bounce at all. All the energy is lost in the collision. So this is actually pretty close to a perfectly inelastic collision. This is a demonstration of a completely inelastic collision. Here, I believe that the product is called the egg splat. It has this kind of sticky membrane, and inside of it there's a viscous, kind of a thick fluid, kind of something that's supposed to look like an egg yolk in there too. It's really disgusting. But when you throw it at a surface, that's what happens. Normally a ball, you throw it at a surface, it would bounce back up at least a little bit. But this doesn't bounce up at all. It's a completely inelastic collision. Today we're going to demonstrate elastic and totally inelastic collisions. I have two carts and a track. The carts both weigh the same amount. Their masses are the same. And they have magnets here that oppose each other. So there's a magnetic force. And so what I'm going to do is leave one stationary and then push the other at a slow speed and see what happens after the collision. So what you can see is that this one that started off moving collided, didn't actually hit it, but the magnetic fields interacted for a very short period of time and transferred all of its energy to the other cart. And we can do the same thing in reverse. It transfers all of its energy to the other one. That's a so-called elastic collision, where there's no energy lost in the collision. During the collision, both energy and momentum are conserved. And when you solve the energy conservation equations and the momentum conservation equations, you find that all of the energy must be transferred from the one to the other. The other way you can do this is in the frame of reference of the center of mass of these two carts. And if I'm capable of pushing them both at approximately the same speed, then they'll hit and leave each other at the same speed that they came together. These carts are different. They have no magnets, but they have some Velcro here and here on both of them that allows them to stick together. So you start with this one stationary and this one moving. Then once they hit, then they move along together at a slower speed than this one was moving originally. This one has 0 energy initially. This one has energy 1/2 mv squared. Once they hit, they move along as a unit with twice the mass and a smaller velocity that you can calculate from conservation of energy. You can also do this one in the center of mass frame. And if you impart the same momentum to this one, equal and opposite momenta to these two, then you can get them to stick and remain stationary. Just like that. That's a totally inelastic or perfectly inelastic collision. Okay, let us now build these into a concept. Define elastic, inelastic, and completely inelastic collisions. Kinetic energy is conserved during elastic collisions. So that's the case of the ball, the black ball that I dropped first in the demo. Dropped it down, it hit the surface, came back almost all the way to the top. So it wasn't actually elastic, but it was pretty close. The ball came up almost to the same height as before. If it had come up all the way to the top, it would have been what's known as an elastic collision. And kinetic energy is conserved. And the collision in that case was between the ball and the surface. And if energy is conserved during that collision of the ball with the surface, then we consider that to be an elastic collision. And you can think about, one way to remember it is just, it seems like an elastic band. If you stretch it, it comes back. That ball was made of a very elastic material that bounced back into its original shape. Inelastic collisions are things that are not like elastic bands. They are, for example, the second ball that I dropped, the second black ball in the demo, had some viscous material inside of it that dissipated energy and was not at all like an elastic rubber ball. Kinetic energy is not conserved. So here's for the elastic collision, here's for an inelastic collision. Doesn't come up quite as high. And in fact, both of the black balls that I used were technically inelastic collisions because they bounced back up, but didn't bounce up as high. A completely inelastic collision is one in which the ball comes down and doesn't come back up. It sticks. And for that one, we showed you the demo with the egg splat. This one, mushy stuff that just stuck and didn't bounce back up at all again. That's called a completely inelastic collision, sometimes called a totally inelastic collision. And in some of my videos I called it a perfectly, depends on which textbook you use, if they call it totally inelastic, perfectly inelastic, or completely inelastic. But the bottom line is it's complete. The energy is lost. They stick together and there's no more kinetic energy after it's done. So when the objects stick together, that's called a completely inelastic collision. Our textbook uses the word completely, and so that we'll stick with that. All right, let's do an example. Car 1 has mass 6,500 kilograms and speed of 0.8 meters per second. 6,500 kilograms, Speed is 0.8 meters per second. Don't want to be running these too fast lest you smash them up. Car 2 with mass 9,200 kilograms. And speed 1.3 meters per second. Overtakes car 1. So car 2 is traveling faster than car 1. Car 2 overtakes car 1, and then it couples to it. They hook, those little latches between the cars connect, and find out the speed of the cars after they become coupled. So this is now before the coupling, and this is after the coupling when they're traveling along together at a common final velocity. Both of them are moving at the same velocity. And I might ask you, before we do the calculation, what you might expect that velocity to be. Would it be bigger than either of those two velocities, somewhere between the two? And I think you might say, well, it seems to make sense for the final velocity to be somewhere between these two. And given that car 2 is more massive than car 1, it might have more of a say on what the final velocity is, and in fact that's true. Let's work it out. m1v1x plus m2v2x initially, well, that's car 1 is 6,500 kilograms, 0.8 meters per second. We're talking about the x direction being toward the right. So both of these have velocities in the plus x direction. Their components of velocity, v1x, are going to be positive. Okay? Plus 9,200 kilograms times 1.3. Then that's going to equal the final momentum of the system, assuming this is an isolated system. This one is very similar to the other ones we've already looked at, billiard balls, man pushing off the woman, etc. The force of collision is going to be huge. And also the normal force and the weight of these cars is going to be negligible because the motion is horizontal and those forces are vertical. And a force that is perpendicular to the motion does no work. So we can ignore the work done by those external forces. And we're going to also ignore the friction of the track. One reason why friction in this case is negligible is that collision is very, very short. And during that very short amount of time while those two cars are coupling together, friction doesn't have much time to do much work at all. But we're conserving momentum. We are plugging in the values. The final velocity of 1 and the final velocity of 2 are going to be the same. So we've actually factored out that final velocity, and so this times this will give the final momentum of 1, and this times this will be the final momentum of 2. Then we can solve this, add those two numbers together, divide by whatever that sum is, and solve for the final velocity of the two cars. It's 1.1 meters per second. Is that closer to 2 or closer to 1? Well, it's 0.2 meters per second less than the initial velocity of car 2, and it's 0.3 meters per second more. And so it's just as we expected, that this bigger, more massive car 2 is going to push its weight around a lot more, in the same way that the man pushing off the woman in the skating rink, the man has more of a say about, he's going to push things around a lot more. Demonstration of conservation of energy and momentum using a ballistic pendulum. And this is one that you will do in lab. So this will be an introduction to what you do in the lab. This is the ballistic pendulum. It will be the subject of one of the labs that you will do. It involves a pendulum and a ball and a gun. So this gun is going to shoot the ball. The ball will get captured and held by the pendulum. And the momentum of the ball will then cause this pendulum to swing up to a certain height. And what you'll do in the lab is to measure that height and then use the conservation of energy and momentum appropriately to study the problem. So what we'll do is place this ball on the end of the gun and then try and cock the gun and then get this pendulum stationary and then pull the trigger and hope for the best. 0, 1, wow, 3, 2, 1. Okay, so what you've seen is that the ball was shot by the gun, captured by the end of the pendulum, and then the pendulum and the ball travel up together to a certain angle. So what you do in the lab is you'll actually measure that angle and deduce the initial velocity of the ball. So not only are we going to do that in lab, we're going to do it right here as an example. It's a great example of how to apply the principles of conservation of energy and momentum. A 0.01 kilogram bullet. So we've actually reversed the direction here and we've replaced the whole metallic structure with a block of wood and a bullet. And the bullet is coming from the left instead of from the right in the video. Then the block of wood is attached to a string, and then the block, swings to a maximum height of 0.65 meters. So that's this height right here. Starts down at 0 and comes up a good fraction of a meter. We want to find the initial speed of the bullet. I'm pretty sure that's what you actually do in lab, is to find that initial speed. You'll analyze it in different ways. So what we're going to do is to divide this problem up into stages and ask about the conservation of energy and momentum during each stage of the problem. Stage 1 is the collision between the bullet and the block. So the bullet and the block is my system. And stage 1 is just to consider the collision between the two. So this slide is devoted to stage 1. Slide 2 is devoted to stage 2, which we'll talk about. So we need events. Just like when in projectile motion, you need 2 events to be able to conceptualize how to apply the equations. So the first event in this case is just before that bullet strikes. So it's a fraction of a nanometer away from the wooden block. And the final event is just after the bullet comes to rest in the block. So we're talking about this instant in time just as that bullet is arriving. That's initial. And then the final event is after the bullet has come to rest in the block. So we're assuming that the block doesn't get disintegrated by the bullet like we did with the ping pong ball and paddle demonstration, but that the bullet comes in and comes to rest and is finally moving together along with the block. So the amount of time between those 2 events is very, very short. But in this particular case, we don't even care how long that is because we're not interested in the impulse. We are interested, however, in the velocities. So we need to ask during that time whether energy and momentum are conserved. Short answer is energy is not conserved and that momentum is conserved. Let's do momentum first. Momentum is conserved if the work done by external forces is negligible. Well, the external forces that act on that bullet while it's getting embedded in the block are going to be very small compared with the internal force of the bullet on the block, which would be huge. And if you doubt that, then put your finger in there right in front of the block just before the bullet hits it. Then you'll believe me. So we can neglect all other forces, gravity, normal force, anything else, And we can say, yeah, momentum is conserved during that period of time because the external forces are negligible. So that's great. Let's go ahead and conserve momentum. This problem is just like the other problems that we've looked at. The initial momentum in the x direction equals the final momentum in the x direction. Well, there's only one of these that's actually moving initially. It's m1, it's the bullet. And its initial speed is, we're calling it v1. So that's the result here. v2, the velocity of the block, is 0 initially. Then finally, the two are traveling along together. So this is the final situation. After the bullet has become embedded in the block, then the block and the bullet are moving along together at a common speed. And that's what's over here. So it'll be m1 times that common speed plus m2 times that common speed. So we can now solve for the initial velocity of the bullet. That's actually what we're looking for, the initial speed of the bullet. So there's the equation. And the trouble is we don't know everything. We know the masses of everything, but we don't yet know the final velocity v1, just after they begin moving up. That's what we need the next slide for. But before we go to the next slide, let's ask about energy conservation during this stage of the problem. Between this instant in time and this instant in time, which happens a fraction of a second later after the bullet is completely embedded. Why is energy not conserved? Because the force of the bullet on the block is a non-conservative force. So that force of the bullet on the block is an internal force if your system includes the bullet and the block. Happy day, it's internal. But energy doesn't care whether a force is internal or external. What energy cares about is whether the force is conservative or not conservative. And it's not conservative, because that bullet there's going to be a lot of friction as the bullet enters the block. That force is non-conservative, and I cannot ignore that force. It's in fact the force that dominates the considerations. So the collision is completely inelastic. We can't conserve energy. Remember, an inelastic collision is one in which the two objects stick together after the collision. So that's another reason why you can't conserve energy. So, but we're happy about conserving momentum. Now, here's the calculation of the common velocity, and we're going to get that from conservation of energy. And how do we do that? Well, now we're talking about stage 2 is the bullet and the block system rise to a maximum height, with the initial event being just after the bullet comes to rest in the block. So this initial event is the final event for stage 1. It's this point here. That's my initial event for stage 2. And my final event for stage 2 is when this block and bullet come to rest at a height of 0.65 meters, reaches maximum height. So now, during this stage, forgetting about the collision, that's over. Now we're just thinking about this as a single entity, and they're going to rise up to a certain height. What's conserved during that period of time? Well, the short answer is that energy is conserved. When is energy conserved? And this is what I'm encouraging you to commit to memory, because it'll help you on the problems, it'll help you on the test. We'll ask some questions about this. Energy is conserved when the work done by what kind of forces is negligible? You say non-conservative. And I say right. Energy is conserved when the work done by non-conservative forces is negligible. Well, what forces are acting on this guy while it's coming from here to here? Let's actually look at all of them. Well, there's gravity. It's weight acting down. There's tension in the string connecting this wooden block to the ceiling. There might be a little bit of air drag while it's pushing through the air, but it's not going very fast. And you might think, wow, that is a non-conservative force, but I can neglect it, like we did in several examples in Chapter 6. So these forces that are really doing much work at all are gravity is certainly conservative. The tension force is not conservative, but the work done by the tension force is going to be zero while it's rising from here to there. Why is that? Because the displacement and the velocity are always perpendicular to that tension in the string. Just like we talked about with the mass on the end of a string. That if the displacement is perpendicular to the force, then that force does no work. So I know this is a lot of trying to get used to this, but hopefully after doing a few problems and doing some practice tests and things, you can start to get a grip on when things are conserved and when they aren't conserved. But the important thing here is that the non-conservative forces are negligible. The only non-conservative force, really a better statement of this is because the work done by, I'm always trying to be careful about saying that it's the work done by non-conservative forces are negligible. This tension is not negligible, but it doesn't do any work. So they're negligible. So we're going to conserve energy. Energy is kinetic plus potential initially, equals kinetic plus potential finally. Happy day. The initial kinetic energy is just the kinetic energy of this guy whose mass is m1 plus m2 times its velocity 1/2 m v12 squared. So there's the initial kinetic energy. The initial potential energy, that guy right here, well, what's that? If we select this to be our coordinate system, x, y, then the height of that object initially at this initial spot, so this is my initial event, here's my final event up here, then initially the height of that is 0. And so mgh will be 0 because the height is 0. I've just simplified my life by selecting a coordinate system so that the initial height was 0. Then finally, we need the final kinetic energy up here. How much kinetic energy does it have up there? Well, it's just swung up to the point and then it instantaneously stopped. So its velocity is 0, its kinetic energy is 0, so that term vanishes. But we do have some gravitational potential energy, and that's m times g times that final height. So that's the final energy. And now we can solve. The m, by the way, that I'm using here is the combined mass. That's m1 plus m2 right here. Okay, so we can solve this equation for v12. How do we do it? The masses cancel. I can multiply by 2. I can take the square root. So I'll have 2 GHF, the square root of that. Plug the numbers in, 9.8, 0.65, that's the final height. And we get the 3.57 meters per second. That's the number that we needed in the previous slide to finish the problem. So let me just go back and note here that in order to find that initial speed of the bullet, I needed this 3.57 meters per second of the speed of these guys after they come together. You might not be able to read that very well, but it says 3.57. You have to trust me on that one. Plug the numbers in, and we get that the bullet speed was 896 meters per second, which is a pretty good size speed. I think you'll have to agree. The reason that that one was so big, that velocity is so big, is that that mass of the bullet is small compared to the mass of the block. So in order to get the block and the bullet moving at this speed, that bullet has to be coming at a really high rate of speed. And you say, well, does this relate to, can you actually work out, your recoil velocity. You've got your gun and you shoot a shotgun shell or whatever. You pull the trigger and you feel that recoil. Can you do that with conservation of momentum? Yeah, sure can. Newton's cradle is another really fun and very popular demonstration. You probably played with these before yourself. This is Newton's cradle. He might have rocked in this cradle as a little baby boy, I don't know. But the idea here is if you release a mass from the side, what happens is that there's a compression wave that propagates through these, and only one ball comes up on the other side. How can you predict that using physics? And the answer is that if you conserve both energy and momentum, you can show that if one ball comes down, then one ball has to come up. You can't have one ball coming down and then four balls coming up with a little bit less velocity. That won't conserve both energy and momentum. Well, what about two balls? Two balls down, two balls up. What about three balls? Three balls down, three balls up. Four balls? Four down, four up. And now for the magic trick of the whole day, five balls. Five down, five up. That's Newton's cradle. Okay, and just another, you can also do two-dimensional problems with conservation of momentum. Billiard ball collisions, for example. Suppose you take a billiard ball, you send it toward the right, it collides with another billiard ball at this point here in the center, and then the two balls go off in different directions. And let's suppose you were able to measure the direction and the velocity, or the speed of, well, velocity includes both direction and magnitude, direction and magnitude of the velocity of one of the balls, and you wanted to know what the velocity, direction, and magnitude of the other ball is. You can do that using conservation of momentum. So it's going to be m1 v1x plus m2 v2x initially equals that same thing finally, and then you're going to do the same thing with y. m1 v1y plus m2 v2y initially equals that same mess finally. And what you have to do is you have to resolve this initial velocity into components, just like we've done a number of times over the last several chapters. So this is VO2x, the initial velocity of ball, I'm sorry, this is ball 2 and this is ball 1. So this is initial O1x. Well, we know that VO1, the speed of the first ball, is 0.9. And we know that this angle is supposed to be 50 degrees. And we want this side of that right triangle. And you look at that side of the right triangle and you say, well, hang on, it's an x component, so it has to be cosine, right? Well, not in this case. You can't always assume that it's going to be the sine or the cosine based on whether it's x or y. It really depends on what the angle is. We know that the angle is 50 degrees, and I want this side of the triangle. Is that side of the triangle the opposite to or adjacent to 50 degrees? And you say, well, it's opposite to, so we need the sine. So that'll be 0.9 meters per second times the sine of 50 degrees. That'll give you VO1x. This is VO1y. And so those will be these guys here. That's VO1x, and this is VO2x. Sorry, I lied. This is VO1y. There's the O, there's the Y. So we've just talked about what those two objects are. V2, let's ask about that. Here's V2, the velocity of ball 2. What are its components? And I might ask you, this velocity V2, does it have a component in the x direction? You say, yeah, sure it does. It's pointing in the plus x direction. Does it have a component in the y direction? You say, I don't think so. And you're right. VO2y is going to be 0. Then you're going to do the same kind of thing on the other side. V final 1 in the x. There's the V final 1 in the x direction. Here's V final 1 in the y direction. And you're going to do a similar thing with V final 2. And we've even broken down this V final vector into its x and y components. So that's how you attack it. Plug the numbers into these two equations, and you have to write out the right-hand sides here. Plug the numbers in and see what you can solve for. Okay, here's a demonstration of a two-dimensional collision. So those of you who have played billiards or pool know all about collisions. And collisions are when one object collides with another. The amount of time for the collision is very, very small. And during that time, the force between these two billiard balls is very high. You can know that by trying to create a collision and putting your finger in between. It doesn't feel so good. All the other forces during the time of that collision can be ignored. Gravity, the normal force, any frictional forces, because the force of collision, the force of these two billiard balls hitting against each other is much, much greater than any other force. So you can get a direct head-on collision like that, or you can get glancing collisions where the balls go off at different angles. Using the conservation of momentum, given one of the angles, you can predict the other angle. So it's a fascinating area of physics, but generally during a collision, the only force that matters is the force of the collision, the force between the bodies. A really good example of the fact that you can ignore all other forces during a collision is during an automobile collision. You could care less about gravity or any other forces when you're colliding with another vehicle.